Okay, hello and welcome back, everybody. So we're still in the finite difference methods section. We're going to move on to two examples so we can see what this kind of looks like in action. I know a lot of you have expressed kind of intimidation about how this is going to require coding, and I just want to point out that coding is an incredibly useful tool for the mathematician. You can't really get away with important calculations in the 21st century without coding. This is akin to 100 years ago being a mathematician and saying that you don't like using a slide rule because you have to use a slide rule to actually be a good mathematician. And I think the same goes for coding. You don't need to be the world's best coder, but you need to know how to do it so that you can accomplish very important calculations when you need to achieve them. So it's not like you're designing software. All you need to do is understand the math and understand enough code so that you can actually implement math. It's like typing in equations to a calculator and hitting enter. It's just your equations happen to be 50 lines long, and that's okay sometimes. There are definitely courses in Python, MATLAB, etc. that you could take to learn the coding. With that said, in very small numbers, you can definitely accomplish finite differences without coding. It's not really a good reason to do it without coding, but if you're extremely intimidated by coding, sure, go ahead and write down a system of 9 equations with 9 unknowns by hand, and then, go to Wolfram Alpha and find your solution to those equations. So you don't need to know how to code to do this in the cases that we're going to handle it in this course, but I would say it's a pretty good idea to think about coding if you plan on doing math for an extended period of time in your life. Anyway, let's move on to this example, 6.2.6. I'm calling it approximate a solution to Laplace's equation on the disk. So here we have Laplace's equation. This is on the two-dimensional disk. I'm just writing it as B01 here because it is the ball centered at 0 of radius 1, also known as the disk. And then its boundary is the circle. It's going to be the boundary of the disk right there. And we're going to try to solve Laplace's equation using finite differences. Now, you probably should be able to handle Laplace's equation on the two-dimensional disk anyway. And this is going back to theorem 5.3.8, where I do actually give you a way of solving this exactly, to an uncalculated integral using Green's functions. I actually gave it to you in any number of dimensions for a ball of radius 1 centered at 0. So you would be able to calculate this if you wanted to, and that's why if I scroll all the way down to the bottom, we can see that we have a nice looking solution. The solution's the one in gray there against the cyan. But you can see a pretty nice looking solution there. That's how I was able to calculate it using that Green's function. Of course, it's probably intimidating that I'm going through the entire example, and you can see just how much there is to talk about with finite differences, but you can actually construct the actual example, and then you can compare your finite differences against it. We're going to go through our steps. If you've forgotten the step-by-steps for finite differences, go back one video. I've got them described there. But in step 1, we just kind of decide on the epsilons. So we're deciding on the differences themselves, right? Every time you see this epsilon, as well as the word finite difference, you kind of want to think about them as the same thing. So epsilon is the finite differences. Because we're in 1, 2 dimensions, we actually have 2 choices of differences that we can take. I'm going to give both of them a difference of 0.5. So I think about it that way. This is my two-dimensional ball. Differences of 0.5 would be at 0, 0.5, 1, 0.5, 1, negative 0.5, negative 1, negative 0.5, negative 1, and then we're going to fill that lattice in. And of course, I could fill the lattice infinitely large, but really we only care about the intersection of the lattice with the boundary and perhaps one extra collection of points on the lattice around that. And so this is really going to be my epsilon lattice here. You can imagine if I increase the lattice size or decrease the lattice size, make it smaller and smaller, you get a better and better approximation of that circle. But for now, we're going to be thinking about that lattice on top of that circle with step size as a 0.5. And that's kind of arbitrary. You just kind of get to decide that for yourself on what you think would be good. I chose a fairly large epsilon here. 0.5 doesn't feel that small, but that's so that we can actually write everything out explicitly, so it's not completely ambiguous how many equations we have. But with this step size, we can actually construct an approximation of the gradient. And actually, I've got a typo here. It's definitely a 2. So we've got a 2 up front, and then we have kind of our finite difference operator in the x direction and then the y direction with step size 0.5. The 2 up front, by the way, is because you really have the finite difference operator step size 0.5 divided by 0.5. So that should really be 2 finite difference operator times 0.5. So that's why I've got the 2 up front. That unfortunately is a 4. But I fixed it in the later lines. Because from this, you can actually approximate the Laplacian. Now that's super confusing, right? Because we've got the same sort of delta going around there. This is what I said in the last video, that unfortunately we use the Laplacian delta and the finite difference delta in PDEs. So that's the Laplacian on the left, and then finite difference deltas over here. Or just as before, the Laplacian is just the dot product of the gradient with itself. So if I have an approximation to the gradient with itself, then the Laplacian is just going to be kind of the square of the finite difference operators added together. And now in step 3, we do want to talk about constructing our epsilon lattice. There I have it in the first picture. And then I've overlaid it on the circle, and you can see there's my lovely collection of points in omega dis. If you've forgotten these definitions, I would go back a video and rewatch that one. There's my collection of 9 points in omega dis. And then if I take really one collection of points around those 9, right, the first collection of points around omega dis is going to be the boundary of omega dis. Boundary omega dis. And it looks like I have 12 points in the boundary. So I've got 12 points in the boundary and 9 points in the center, where really it's always just the points in omega dis that we don't know the value of phi at. On the boundary, we definitely know the value of phi. So at that point, I just kind of eliminated the rest of them, and we really just want to think about this picture here as the primary picture that should be in our minds of points that we are going to work with. So this is constructing omega dis and its boundary, and I have an explicit construction of both of them here. If you really need to see the explicit construction, it's kind of pretty frustrating to write that down. But in step 4 then, in step 4, we always want to construct the finite difference equation, which approximates the PDE. So I'm going to take my points in omega dis, and at each of those points, I use this approximation to the Laplacian, and then I make my special choice on epsilon, plus or minus epsilon, right? So let's recall that this approximation to the Laplacian was really the finite difference in the x direction divided by 0.5 squared, and then the finite difference squared in the y direction divided by 0.5 squared. And because of the plus or minus in front of this epsilon here, we really have a plus or minus here, and a plus or minus here, also in the denominator, but since it's squared, it actually doesn't play too much of a role. But we're going to want to be thinking of constructing this operator and asking ourselves a question. We ask the question, which interior points are these well defined on? Right, why is there a specific collection of interior points that this is well defined on? Well, it's because when we have our 9 points of the omega dis, 1, 2, 3, 4, 5, 6, 7, 8, 9, because the Laplacian is second order, we need to compare 2 points against 1. So that's a total of 3 points actually. And so what's actually going to happen is there's going to be 2 points compared against 1 in the y direction, and then 2 points compared against 1 in the x direction. And so you're going to have shapes like that that need to be incorporated with this approximation to the Laplacian. And because we have boundaries, we can actually, right, we've got these extra boundary points here that make our life a little bit easier. We can compare to the boundary points. We don't just have to worry about allowing those 2 points to compare. So I could do 1, 2 points, compare these 2 to this boundary point, and then I can compare like these 2 to this boundary point in the x and y directions. But basically what we're thinking about is that we have a sort of L shape. And that's why I've got this L shape here, where I say we really have a choice over all sorts of different L shapes. In some sense, the corner of each L is the point we're actually analyzing, but we need 2 neighbors in either direction to give us an approximation to the second derivative. So the finite difference operator, and of course it's because it's squared, compares 2 points to the original. So there's 2 steps in any direction that we need to be able to fit this operator. This is where we choose our plus minus sizes for epsilon. So I'll try to describe what's going on in these pictures. In some sense, if we're moving to the right, that's a plus epsilon, and that's in the x direction. And if we're moving down, that's a minus epsilon in the y direction. And so here, we're moving to the right, that's a plus epsilon in the x direction. We're moving up, that's a plus epsilon in the y direction. And that can continue. So that's negative x, negative y, positive x, positive y, positive x, positive y, negative x, positive y, positive x, negative x, negative y, negative x, positive y, and so on. Now, what I've done is this is 9 equations worth of approximations to the Laplacian, right? Every single one of these L-shaped structures is an approximation to Laplacian at its corner. So I've got 9 approximations to Laplacian. And the reason I chose 9 is because how many interior points did we have? We had 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm trying to construct a system of 9 equations with 9 unknowns. Why does an approximation to the Laplacian assign itself a single equation? Well, if I go back up to what I'm actually constructing, this as a system, that's an approximation to the Laplacian. That's a 0. So the fact that I'm assigning every approximation to the Laplacian the value 0, that means I'm gaining 1 equation for free. So every time I write down an approximation to the Laplacian, as in these pictures, I'm gaining 1 equation. Hence I need at least 9 of them to give me a system of 9 equations, 9 unknowns. Now you may be curious what's going on here in the second line where it says, phi of xy is equal to tilde sign x times y. That's because this tilde sign is because I'm working on the discrete boundary, where if I look up here, my discrete boundary, like I said before, is these 12 points sitting around the circle. And we know from the PDE that the value of sine, or the value of phi, achieves sine on the boundary itself. But when we're doing the finite difference method, we actually don't care about the boundary itself, we care about the value at these extra points. And so we have to project the points onto the boundary to find their answers. So because our system of 9 equations is going to include some of these points, I'll scroll back down and you can see where it includes these points on the discrete boundary. So there's our 9 equations visually. You can see this term, this term, this term, this term. That's it for these 9. Oh, actually both of these, those 2 as well. Those are all boundary values. So we need to know, really tilde sign at those values. We have to assign phi at each of those values some sort of number. And so we do that in step 5. But before we get there, I'm going to translate this collection of 9 pictures, which really does represent this collection of equations, which approximates the original PDE. I'm going to assign those actually a numerical set of 9 equations. So for each of these 9 pictures, I'm going to extract the equation that the picture represents. So I'll jump back up in a bit, but what I'll mention right now is that what I'm highlighting right now, is associated to the top left picture above. I want to describe how that's true. So if we look at the numerator here, this numerator really is the finite difference in the x direction with step size 0.5 squared, and then there's my, divided by 0.5 squared. And it's associated to the top left finite difference above. So let's go back up here. There's the finite difference in the x direction squared. What is the corner that everything's being compared to? This is the point, negative 0.5, positive 0.5. So it's really the value of phi at this point that I'm going to be constructing everything on. I'm going to scroll back down here. There's phi at that point. And then this is my finite difference operator squared, giving me 2 other terms. And then it's divided by 0.5 squared to approximate the Laplacian in the x direction. We've got the same thing going on in the y directions here, but you'll notice that the denominator has this negative 0.5 squared in it. And if we actually look at the direction that the y's are moving in the numerator, they start at a negative and they start to move positive as we move to the right, which is actually in the opposite direction of the regular finite difference operator. So that's the fact that we've chosen a negative epsilon direction, because this is pushing downwards. And so what that first equation has done is it's constructed this direction and added them together as approximations to Laplacian, and it said, by the way, that's equal to 0. Why is the approximation of Laplacian equal to 0? It's from the original PDE, where the approximation of Laplacian should be 0. So that's how I grab the first picture and end up with the first equation here. I'm going to do that with every single picture. And what I've done is I have color coded in cyan. These are the boundary terms that showed up in each of those pictures, as well as in, the yellow, we've got the interior terms that we don't know. So there's my boundary terms and my interior terms that we don't yet know. But what I've done is I've just translated every single one of these, both in the x and y directions, equals 0, is going according to one of these L shapes that I've been able to draw up above. So there's a positive y direction, a positive x direction, where we're comparing ourselves to the point negative 0.5, 0. And here you can verify that the point is negative 0.5, 0. Okay, so you do that with all 9 of those pictures, and you have a nice system of equations. But like I mentioned already, we actually want to know these boundary values, because those are not included in our 9 unknowns. These should be considered known values. From the boundary condition. So that occurs in step 5. So in step 5, we're going to figure out what those values actually are. What I have to do is I have to map each of those points to its nearest neighbor that's actually on the boundary. So this is the nearest point actually on the original boundary. So when I had my circle and I had this lovely collection of points around the circle, what I'm doing with this negative 0.5 and 1, which is negative 0.5 there, 1, it's that point, what I'm doing is I'm projecting it onto the circle. I'm saying, what is this point on the circle? And it's not too hard to do that, right? You're just going back basically to calculus 3 into projections. So you're going to find that point. You can do that with each of these 12 points on the boundary. In fact, I only needed 6 of them because only 6 of the points play a role in the 9 equations I chose. So I really do that with 6 of them. And then I just evaluate. I'm saying that phi at this discrete boundary point is going to be the value of sine at the actual boundary points, sine xy. And that goes all the way back to the original PDE, which stated that sine xy was the value on the boundary. So that's where I'm going to construct the value of of phi on the discrete boundary points. And then what I'm going to do to make this system look a little bit more clear, right? So I have this giant system. What I'm going to do is I'm going to replace all of these with their values I just calculated. So all of those 6 numbers with the values they just calculated. I replace each phi with a k, just the coefficient k or the variable k, where I'm assigning to k's these specific subscripts. I'm basically treating it like a matrix of 9 points and giving the k's the subscripts. That now gives me the equation where I've simplified my denominators as well, and everything looks a little bit more like maybe a computer can handle it, or even your calculator could handle it as a system of 9 equations and 9 unknowns. So we got a system of equations, 9 unknowns here, and all we have to do is solve for them. So we go ahead and use a solver. System of equations solver. And what we see is that k11 equals 0.1 plus 1.514k33. And that is the point at which you should recognize 9 equations wasn't enough because we don't have uniqueness. Linear systems are interesting, right? You either have a unique solution or you have infinitely many solutions if you're degenerate. You never have like 2 or something. So we don't have enough equations for unique solutions. That's not necessarily a bad thing. It just means that we didn't choose a good collection of 9 equations from the beginning. It means that one of these is implicitly dependent on the other 8. Not the end of the world. But the way we fix it is that we just add 1 more. And we repeat until, we do end up with a unique solution. And for linear problems, thankfully, you can guarantee that these unique solutions do exist in a lot of situations. So you just keep adding equations until a unique solution exists. In this case, we do add just 1 more equation. I've chosen that shape of an L. And once you add that into the system, it's associated to this equation, by the way. Once you add that equation into the system, you do find a unique collection of k11 through k33 after using your numerical solver on 10 equations, which again is a lot of zeros. So that sure was a lot of work to get a whole bunch of zeros. You only have 4 non-zero terms. And those 4 non-zero terms correspond to, I believe, 1, 2, 3, those 4 points in this problem. And so this has given me a value of phi at each of those 9 points, including those 4 corner shapes where they are non-zero. What we can do in step 6 is we can use an interpolation. So we're basically going to interpolate phi, interpolate these values, and the boundary values with some sort of interpolation procedure. And this is always an optional step because some people don't like interpolation procedures. But if we do, then the following in the cyan, right, so the cyan color is interpolated, and the gray is exact. And so even with not just 9 unknowns, right, we've put 9 unknowns into the center and then constructed our boundary as an approximate boundary. Once you interpolate it, you get a really, really nice solution. So that's really, really nice to see that the approximation gets so good so quickly, even if the price we had to pay was kind of constructing a system of 10 equations, 9 unknowns, making sure that, you know, all of these L shapes were constructed so they didn't extend past the boundary. It is a lot of work. That's why coding can be helpful. As evidenced by me in this example, though, you definitely don't need to necessarily code anything until the very end. A little bit frustrating for me, but you know, I wanted to make the example explicit for all of you, so it would make a little bit more sense. Now, what I've done in these 3 pictures in the center is I've showed what it looks like when you choose a smaller and smaller epsilon. So choosing epsilon is 0.1.1, you can kind of get this pretty good approximation of the circle. Choosing epsilon 0.5 or 0.05, you really start to fill in the circle, and your boundary gets closer and closer to being truly more one-dimensional. And then when you let epsilon be 0.01, my computer program didn't even attempt to give any white space in there. So everything is like basically perfect to the circle when you let epsilon be that small. So if you can manage to get the code working correctly, so all you have to do is increase or decrease the size of epsilon, which increases the number of nodes, and then the code outputs your answer, you're going to get a really good approximation really fast. You can imagine that there's just no way for anything to differ from the exact answer at that point. So it's really, once again, it's just like with Riemann sums and anything else, you're going to approximate a continuous solution by a limit of discrete solutions, and a limit of a very large number of discrete solutions is going to be really close to the actual answer. Moving on to the last example in this section, calling it an approximate solution to the nonlinear quote-unquote heat equation. So what I've done here, I want to show that, you know, we can use these on nonlinear problems that nothing else from the book can really tackle. Maybe Cauchy-Kovalevskaya, right? But nothing else with chapter 6 in the book can tackle. So there's a pretty nasty nonlinear term here. It's phi squared times 2 derivatives in the x direction on phi. So that's a pretty bad nonlinear term. And we're still going to see if we can get something to work out on this solution. Let's make it clear what the boundary looks like here. So we've got a t equals 0, and then we have x and 0, 1. So if this is my time direction, this is my x direction, what I'm going to do is I'm going to take t equals 0, I'm going to take the x equals 0 point and the x equals 1 point. There's t equals 0, and then I move forward in time, so everything kind of extends to the right from there. So my domain is going to kind of be the interior of all of this. Meanwhile, the boundary is what I've got in cyan there. So that's what we're going to want to think about with our domain and our boundary. This actually makes our life pretty easier. Our life gets easy when omega and its, you know, boundary are flat. This is because the lattice will agree with the boundary. So I'm not going to have to play any of those games when I construct my lattice, right? The lattice will just necessarily align with these boundary points. That's going to make my life easier when I have questions about, you know, the discrete boundary. It's just going to be exactly the values on the boundary itself. With that said, we should just go through our steps. And so our step 1 is always just construct an epsilon that we think is going to be useful. Obviously, you would want to tune that epsilon higher or smaller and smaller as you get a better and better approximation. And in this case, what have I done is I've actually taken this is the t direction first and then the x direction second. I've taken the x direction to be half the size of the t direction. And the reason I chose that is coming from the order of the derivatives, right? So the t derivative is first order, so my finite difference method in t will be divided by a 0.5. The finite difference in x will be squared, divided by 0.25 squared. But the numerators here and here, because this is a second derivative in the numerator, it's going to be taking 2 steps. So there's really going to be 2 steps of a 0.25 in the x direction. So you'll have a 0.25 times 2, you'll really have a 0.5 difference in the x direction. So I wanted the overall difference spacing to be the same when I kind of construct that L-shaped thing that we have in the last case as well. So that's why I gave t kind of twice the size of x in my epsilons. Coming from that, though, you can get the partial derivative in time approximated by this finite difference term, and the second partial derivative in x approximated by that finite difference term with the square on it, because it's the second derivative in x. And then in step 3, we construct our lattice spacing. So our lattice spacing is given on there, and if we want to actually construct the discrete domain, there's my 6 points to my discrete domain. Why have I stopped at 6? I did mention at the beginning, even though I didn't do it verbally, I did say through the future time t equals 1. So you can imagine technically the domain is infinite in the time direction, but you're going to have to decide how far out you want to approximate to. So I said to approximate to t being 1. That kind of stops my discrete domain at this, t equals 1 point right there. And so those are the 6 points in my discrete domain. And I can look at my discrete boundary. It's just going to be the collection of points around the discrete domain. And now this is interesting, right? Because we do not have no boundary to the right of our omega dis quote unquote endpoints, right? Because we could have kept pushing these interior points to the right. There's not actually a boundary there. We just decided we were going to be content approximating this up to t equals 1 second. So there's not really a boundary over there, and so you just want to make that clear when we construct the discrete boundary that we're not including points on the right. And so that's going to be the discrete domain and discrete boundary. At this stage, though, it's everybody's probably least favorite part, is to actually construct our system of equations. We're going to want to construct, really, we're going to need 6 equations, right? Because there are 6 points that are unknown on that discrete domain. We're going to have to construct the 6 equations from this approximated PDE equation. And so because of what I kind of mentioned, we're going to be moving 1 time to the right in t and 2 times up or down in x. We need to construct 6 equations where here's me moving to the right in t, twice up in x, to the right in t, twice up in x, right in t, twice down in x, right in t, twice up in x, right in t, twice up in x, right in t, twice down in x. So you just have to fit, that sort of operator. Once again, this is a representation of our finite difference operator. You got to fit that in to the total number of points that you actually know. And we need at least 6 of these because we have 6 unknowns. These are the 6 that I chose. Of course, you can always choose more than 6, but we're going to start with these 6. And as before, I'm translating directly, right, the difference in time into my equation. This is the difference in time, setting it equal to the difference in x, which is a Laplacian, right, the approximate to Laplacian in x. And then this term, phi at a point squared, comes from the PD itself. I'm using the point that corresponds to the sharp corner, right? The corner is where you're evaluating everything from. And so you take the value at that point and you square it because that corresponds exactly to the original PD itself, where it has phi squared right there. So you're just translating absolutely every term you're talking about in the PDE to its individual points here, and then constructing the system of 6 equations. Now, once again, I've color-coded these. These are the terms that showed up on the boundary above. So we should be able to find exact values of those terms because they lie on a boundary and everything else is an unknown. And I can do that here because the boundary, in fact, exactly aligns with the regular boundary. So I just go back up to my original equation. Here it is, right? If I go up to my original equation, you can find the boundary. It's right there. And I can just plug those values in to figure out what they're supposed to be. When I plug them in to find out what they're supposed to be, that's in step 5, by the way, I find 0.177, 0.5, 0.53, 0.10. And if I once again relabel my 6 interior points as like K11, K12, K21, K22, K31, K32, the 6 unknowns. If I relabel those and replace everything in the way that it should be replaced, I end up with that slightly simplified version of 6 equations and 6 unknowns. Now, I do want to comment something very important when we're dealing with nonlinear equations. Nonlinear PDEs give rise to nonlinear systems. And nonlinear systems can behave quite unfortunately sometimes, right? So this is nonlinear because we can see all these square terms showing up. What is everybody's favorite nonlinear equation that doesn't have a solution, at least in the reals? X squared plus 1 has no solution in R. So x squared plus 1 equals 0 has no solutions in R. There's an okay chance that some of these nonlinear systems you construct with finite difference methods will have any solutions. But the other version of this, x squared, say x squared minus 1 equals 0, has 2 solutions in R, which means half the time you're going to construct these, you're going to find non-unique solutions. This is still true for PDEs. There's non-unique solutions to PDEs as well, certainly with nonlinear PDEs. You just have to be careful because a lot of times we look for a unique solution and we may not get them. So in this case, we do find out that this system has 2 real solutions. You'd be like, okay, maybe if I add another equation, it's always within the realm of possibility that I can just choose another L shape here and add a 7th equation, try to get a 7th equation to compare everything to, and then maybe that reduces the number of real solutions from 2 to 1, and all of a sudden you have uniqueness. That doesn't happen here. You either have 2 or you have 0, depending on how many equations you choose. And so we're going to stick with 2, and we're just going to choose the quote-unquote better one, which doesn't make a lot of sense. I realize it doesn't make a lot of sense. There's a lot of intuition that goes on in numerical methods. So you just have to look at the solutions to both and figure out which one, the way I say it, makes more physical sense. This is a heat equation, or a version of a heat equation, and so we kind of expect things to decay over time. And so what I've done is I've chose the solution of the 6 k values, which correspond to the 6 unknown values of phi, evolving over time, where we see a bit of a decay effect. This is why the intuition of PDEs is quite important. You want to be content about knowing heat, wave, Laplace's equations, etc. So we've got a little bit of intuition, and now when I interpolate in step 6, my interpolated solution against the one in gray, which is the actual solution, we see that it meets the values almost perfectly right away in time. And then if we move forward in time, it does differ a little bit, right? It kind of has that peak hanging out in the middle. That's because that's at the t mark. It takes until 0.5 seconds for the term in the middle to change. But once you wait those 0.5 seconds, the term in the middle does start to fall. And you see, like, even, over time, it does serve a fairly good approximation still. But you have to have that physical intuition to say, this is basically a heat equation, so I'm going to choose the collection of k's from solving my system that agrees more with my intuition. And when you do that, you do get really an okay approximation. And you can imagine with more nodes, you would get an even better approximation. But that's kind of 2 examples. I realize, watching it this way, there's me doing examples of more and more nodes on this kind of square-shaped domain. I realize just kind of working through it this way doesn't make a lot of sense. You really have to sit down and just work everything through either by hand or on a computer to make finite differences understandable. I would have this, this book open while you're trying to do that and just try to redo both of these examples from basic principles, just thinking about it yourself. How do I want to solve this using finite differences? And it will make sense as you practice more and more. It's just not the easiest thing to really write down step by step when it's much more of an intuitive and also coding problem. So I hope that's enough. Talk to me in class if it's not. Anyway, I'll see you then. Bye.